System lectures. In this video, I'm going to discuss the Routh-Hurwitz criterion and the Routh array. Now, before we just jump right in, I want to give you a little bit of background knowledge so that you understand why this method was developed and how it's used in classical control theory. Now, if you've been following along with my videos or already have a basic understanding of classical control, then you should know at least two things right now. The first is that in order for a system to be stable, all of the roots of the characteristic polynomial need to lie in the left half plane. And since the characteristic equation is the denominator of the transfer function, then the roots of the characteristic equation are the exact same as the poles of the transfer function. And these roots all must lie to the left of this vertical imaginary line, or all negative real components, in order to have a stable system. I'll briefly explain why that is right now by looking at a transfer function with a single pole, 1 over s plus a, where a is a variable and it can either be positive or negative. And in this case, the root of the characteristic equation is s equals negative a. So when a is positive, s is negative, and when a is negative, s is positive. Now we can take the inverse Laplace transform of this transfer function to get the time domain representation. And this is e raised to the root times t, and you can either write the root as negative a or s, whichever you prefer. Let's take the case where a is positive, and since s is negative, this root exists in the left half plane. And if you plot this in the time domain, you'll see that the signal will tend towards 0 as time approaches infinity. And this is stable since any signal into this transfer function will ultimately die out and the system will be at rest again. However, if a is negative, or the root is positive, then the response will blow up into infinity, which is obviously unstable. Now we can stack any number of these poles up to produce a transfer function of higher order. I'll write a transfer function here consisting of 3 separate poles, 2 in the left half plane and 1 in the right half plane. But we can always simplify a transfer function written like this using partial fraction expansion, which in this case turns multiplication into a summation of 3 separate single-poled transfer functions, all with different constant gains. And when we take the inverse Laplace of each of these, we see that the response is the summation of a bunch of different exponentials. And no matter how stable most of them are, all it takes is one to blow up to infinity to make the whole transfer function unstable. And this is why even if a single root is in the right half plane, your entire system is unstable. So we know that we can determine the stability of a system by solving for the roots of the characteristic equation. But the second thing that we know is that calculating the roots of a system for anything larger than a second-order polynomial becomes time-consuming and possibly even impossible in closed form, as would be the case if you were given this fifth-order polynomial and asked to solve for the roots. So your question might be, how can I determine stability of a higher-order polynomial without solving for the roots directly? And one of the ways that you can do this is by using the Routh-Hurwitz criterion and the Routh array. Now, going through the proof of the Routh-Hurwitz criterion is beyond the scope of this video, but I will cover it in a future lecture if there is enough interest in seeing it. The Routh-Hurwitz criterion states that all roots of a polynomial lie in the left half plane if and only if a certain set of algebraic combinations of its coefficients have the same sign. And this statement, a certain set of algebraic combinations, is really just a cryptic way of saying that you perform the steps to fill out the Routh array. The great thing about the Routh array is that you don't have to actually solve for the roots of the characteristic equation. It allows you to assess stability just by looking at the coefficients of the polynomial. Now, when you're trying to assess the stability of a large-order polynomial, the first thing you should notice about the coefficients is their sign. If all of the signs are not the same, then you can state instantly that the system is unstable. In this case, the coefficients are both positive and negative, so it's unstable. Now, if every single sign of each coefficient is negative, then you can always multiply that transfer function by a gain of -1 just to get all positive values. Remember that in order to solve for the roots, we're setting this equation to 0, and we can always divide out that -1. Therefore, from a stability point, there is no difference between all positive and all negative values. So in general, I'll refer to all the same signs as just being all positive. Therefore, I can say that if any coefficient is negative, then the entire system is unstable. Let me explain why. If you build up a transfer function with a series of poles, then the only way to get a negative coefficient is to have at least one pole exist in the right half plane. If all you have are roots in the left half plane, then you only have positive values in the characteristic equation, and there's no way to get a negative coefficient out of that. So if you have a characteristic equation with at least one negative coefficient, then you can instantly state that that system is unstable without having to go through the process of filling out the Routh array. However, you can have all positive coefficients and still have either a stable or unstable system. Let's demonstrate with this transfer function. The first part has roots at 1/2 plus or minus j times the square root of 3.75. The second has a root at -2, and the third a root at -1. This system is clearly unstable since there are two roots in the right half plane. You can see this from the positive 1/2. However, when we multiply all of these out, we get one polynomial with all positive coefficients. So this just goes to show that you can have an unstable system with all positive coefficients. And if we were given this system in this form, we could use the Routh-Hurwitz criterion to determine if the system is stable. And we would do this by filling out a Routh array. The Routh array is a table that can be populated with the coefficients of your polynomial with a few simple rules. The first step is to set up the table structure. When completing this table, I'll refer to entries in this direction as rows, and entries in this vertical direction as columns. Now the number of rows depends on the order of the polynomial. To start, you need to write the polynomial in powers of s that are descending. So in this case, you would start with s to the 4th, then s cubed, and then s squared, s, and then finally you would just end with the constant. And in the Routh array, the row labels start at the highest order, in this case s to the 4th, and count down to the 0th order, or 5 rows total. And the number of columns also depends on the order of the polynomial, and it's determined in this manner. Write the first coefficient in the first row and first column. Then write the second coefficient in the second row, first column. Proceed filling out the first 2 rows following this up and down pattern until you reach the end of the polynomial. So in our case, we'd start with a 1, then 2, then 3, 10, and 8. And if you've done this correctly, you'll see that you've placed every other coefficient in the top row, starting with the first coefficient, and then the alternates in the second row. Now there's a side note that I want to cover real quick. If there's no value for a particular power of s, then that coefficient is 0. And make sure you write a 0 in place for it because you need this in the table. And in this case, there's no s squared coefficient, so when you're filling out the table, you would just put a 0 in that place. And that's because s squared still exists, you just don't typically write it in if it has a coefficient of 0. Alright, at this point you've set up the table and you've populated the first 2 rows. Now to fill out the bottom rows, you need to perform a series of repetitive math operations. Now there are several great resources on the web explaining in mathematical terms how to go about filling out the rest of the rows, and I highly recommend you check them out. I've left some links in the description below. However, I personally like to imagine it as a pattern that I'm filling out rather than an equation. And if you'd like to get the math behind the pattern, then you can just visit one of those links. Let's say you're given a 6th order polynomial where each power of s has a different coefficient, a through g. You can set up your table from s to the 6th and go all the way down to s to the 0. And if your polynomial is written in descending powers of s, you can write the coefficients in the up-down pattern that we discussed up above. Now at this point, each entry in the table can be calculated from entries above it exactly in this manner. For this red box, it would be b times c minus a times d all over b. And if you think of this as a pattern, it traces the number 8. You start with the b, you multiply by c, you subtract a times d, and then finally you divide by b. Now you can use this pattern to move to the next column, but you stretch out that 8 and perform the exact same sequence. So for this blue box, you would start with the b, and you'd stretch the 8 out to the e minus a times f, all divided by b. Notice that the left side of the 8 is always the first column, and the right side just keeps expanding as you move right through the columns. Once you've reached the end of the columns, you can drop to the next row and perform the exact same steps. In this case, the fourth row would just be red times d minus b times blue, all divided by red. And then stretch out the 8 to get pink, and then stretch it out again to get the next one, and then just keep repeating this pattern. And once you have the entire table filled out, you can count the number of roots in the right half plane by seeing how many times the values in the first column changes sign. Remember that any 0 in the right half plane means the system is unstable, so all you need is for the value to change sign at least once and you know that the system is unstable. So let's use this pattern to fill out the Routh array from above and assess stability. We take 2, we multiply by 3, and we subtract 1 times 10 and divide by 2. You can see that 8 is minus 2. We stretch it out and get 2 times 8 minus 1 times 0 divided by 2 is 8. Of course, these last two entries are both 0. Now we drop down a row and we say minus 2 times 10 minus 2 times 8 divided by minus 2 is 18. Stretch out the 8 and you get 0. Finally, we go down to the last row, we do our calculation, and we're left with 8. I find this pattern recognition, rather than memorizing a bunch of equations, simpler to fill out the Routh array. We can determine the number of roots in the right half plane by looking at this first column. I'll rewrite it here to make it a little clearer. You can see that the first 2 are positive, then negative, followed by 2 positive values. And you can see that it changes sign between 2 and negative 2, which means that there's a root in the right half plane, but then changes sign again between negative 2 and 18. So what we can deduce from this is that there are 2 roots in the right half plane out of the 4 roots in this system. And since there's at least 1 root in the right half plane, we know that this system is unstable. And this is exactly what we would have expected since we built this transfer function with 2 roots in the right half plane and 2 roots in the left half plane. So the Routh array worked for us and we never had to solve for the roots directly. But at this point we already know the basic fundamentals for how to set up and populate the Routh array. So in this video I want to describe 2 special cases that can arise when you're filling it out. But before I begin, I want to just blaze through a quick example on how to set up and fill out the Routh array. This is just a recap from the last video. Let's say you're asked to determine the stability of a system who has a characteristic equation that is s to the 4th plus 2s cubed plus 3s squared plus 4s plus 5. Since this is a 4th order polynomial, you can set up the Routh array by starting with the first row at s to the 4th and ending with the last row at s to the 0th, or 5 rows total. Now you can populate the first 2 rows by starting with the highest order coefficient and zigzag up and down, adding each coefficient of the descending powers of s. And at this point you can start filling in the rest of the table by remembering the figure 8 method, or 2 times 3 minus 1 times 4 divided by 2, which is 1. And to move to the second column, it's as simple as just stretching out that 8 and performing the same steps. 2 times 5 minus 1 times 0 divided by 2 equals 5. And when you reach the end of the columns, you can move down to the next row and start it all over again. And once the entire table is filled out, you can count the number of roots in the right half plane by counting the number of times the sign changes in the first column of the table. In this case, there are 2 roots in the right half plane because the sign changes once between 1 and minus 6 and a second time between minus 6 and 5. Therefore, this system is unstable. Alright, enough of the recap. Now let's get into the 2 special cases that I mentioned that you can come across when filling out a Routh array. The first case is when there is a 0 in a row with at least 1 non-zero element appearing later in that exact same row. Let me show you a few examples of what I mean by this. Say you were given a polynomial whose coefficients created the Routh array like this. In this case, there's a 0 in the second column of the first row and a non-zero, or a 4, in the last column. So this meets the criteria for our special case. Now in the second example, the first column has a 0, but it's also followed by a non-zero element. Same exact thing. Now when this occurs, the system is always unstable, because completing the Routh array will always result in a sign change of the first row. And so if you're only attempting to assess stability of the system, then you don't need to complete the rest of the table at this point. But if you're interested in the number of roots located in the right half plane, then you can complete the table like this. But first, let me rewrite that second example a little bit bigger over here. So when you come across a 0 followed by a non-zero like we see in this third row, you replace that 0 with the Greek symbol epsilon. Complete the array using epsilon in its place. And once you finish completing the table, you can just take the limit as epsilon goes to 0. In our case, the first two rows don't change at all. The third row, that 0 becomes epsilon, which is ever so slightly positive, so I'll write that as a 0 plus. Then, in the fourth row, this can be rewritten as 4 minus 10 over epsilon, and so as epsilon goes to 0, this tends to go to negative infinity. And now in this system you can see that we still have two unstable roots, or two roots in the right half plane. Now if you don't mind, let me just quickly go into an unnecessary side note on why we use the Greek letter epsilon. In several branches of mathematics and computing, epsilon is used to represent an arbitrarily small number. So if you think of the smallest number you can, epsilon is even smaller. However, it is still greater than nothing. In computing, where numbers are represented digitally, machine epsilon refers to the rounding error in floating point arithmetic, and therefore the smallest number that can be represented on a computer before being wholly consumed by rounding error. For double precision arithmetic, which many computers run with, the machine epsilon is 2.22 times 10 to the minus 16th, so that's a pretty small number. Okay, let me show you just one more example of this. Starting with this polynomial, s to the fourth plus s cubed plus s squared plus s plus 1. We can fill out the Routh array just like we did above. But now you can see that in the third row, the first column is a 0, and the second column is a 1. And this satisfies our condition for the special case, and it also states that this system is unstable. You can say that instantly. But we still want to know how many roots there are in the right half plane, so we replace the 0 with epsilon and continue filling out the array. And when we take the limit as epsilon approaches 0, the fourth row becomes negative, the fifth row becomes positive again, proving that this system has two roots in the right half plane. And that seems simple enough, right? Well, let's take this one step further. The second special case is when there is an entire row of zeros, and not just a single 0 in the row. I'll demonstrate this special case and what to do with it with this polynomial. S to the fifth plus 2s to the fourth plus 6s cubed plus 10s squared plus 8s plus 12. And let's fill out the Routh array by populating the first two rows, and then we'll populate the other rows using our figure 8 method. But when you get to the fifth row, or the s to the first power row, that one becomes all zeros. Now before I explain how to continue filling out this table, I want to just address what this means, as there are only a few root locations that can cause a row in the Routh array to be all zeros. When you come across this, it means that you have a polynomial with roots in one of three situations. Either you have two real roots that are equal and opposite in sign, you have two imaginary roots that are complex conjugates of each other, or you have four roots that are all equal distant from the origin. You can see that in all three situations, they're just a reflection about both the real and the imaginary axis. Now here the first and third root patterns both have roots in the right half plane and are therefore unstable. Only this pattern in the middle has roots that are not in the right half plane, but since they exist on the j-omega axis, the system is marginally stable. So when you encounter a row of all zeros, at a minimum you can assert that the system's marginally stable, but it's possible that it's unstable. Now you can determine this by completing the rest of the table in this manner. Call the row directly above the row of zeros the auxiliary polynomial. Well, technically these are the coefficients of the auxiliary polynomial. To find the powers of s that go along with them, begin with the power of s that starts the row, and then skip every other power until you reach the end of the row. For example, the auxiliary polynomial coefficients are 6 and 12, and since the row is the s squared row, you would write the auxiliary polynomial as 6s squared plus 12, or you can simplify it by dividing out 6 to just be s squared plus 2. And for simplicity, I'm going to call this auxiliary polynomial p. Now take the derivative of this polynomial p, and you can replace the row of all zeros with these new coefficients. In this case, the derivative is 2s, and you can replace the row of all zeros with this. So the first coefficient is 2, and then there are no other coefficients afterwards, so the rest of it is just 0. Now you can complete the table, which is just 2 times 12 minus 6 times 0 divided by 2, which is just 12. And since there are no sign changes in the first column, you can conclude that there are no roots in the right half plane, and therefore this system must have some number of roots on the j omega axis, or this second situation. But we can take this one step further still. If and only if there is a row of all zeros in your Routh array, then the auxiliary polynomial exists, and that auxiliary polynomial divides into the original polynomial with no remainder left over. That means that this is a factor of the original polynomial. So I can write this in an equation like this. The auxiliary polynomial p of s times some other polynomial equals the original polynomial q. And this is powerful in determining how many roots exist in the left half plane, the right half plane, and on the j omega axis. We can find what this r is by doing polynomial division. Or in other words, we can take q of s, divide it by p of s, and you'll get r of s, or the remaining polynomial. So let's start with our original polynomial, which I've copied here, and divide it by s squared plus 2, which is the auxiliary polynomial. Now at this point I'm going to skip through this part pretty quickly, since I'm assuming that most of you know how to do this division already. However, if you don't know how to do polynomial division, or you've never seen this before at all, I worked out this entire problem without skipping any steps, so hopefully you can just play this part slowly to figure out exactly what I'm doing. You can see that we're left with a polynomial r of s with no remainders left over, and that means that both r of s and p of s are both factors of q of s, or our original polynomial. Now remember that this is only true if there's a row of zeros in your Routh array. Otherwise you'll be left with some non-zero remainder. Now at this point we can state that any part of the Routh array that is above the auxiliary polynomial goes with our other factor r of s. And since there's no sign changes at that point, we can state that r of s is a stable polynomial. And the number of sign changes after the auxiliary polynomial predicts the number of roots in the right half plane for the auxiliary equation. And this is going to go a long way towards determining where the roots exist, which we know from our three situations above that the auxiliary polynomial is marginally stable. But since we factored this a little bit, we can now solve for those roots directly from the auxiliary polynomial. In this case, the roots are at plus or minus the square root of 2 times I, which are two imaginary roots that are complex conjugates of each other. That is, that they exist on the j omega axis. And this is exactly what we expected from our situations that we wrote out above. All right, let me just summarize real quick so that hopefully it's a little bit easier to remember. In our first case, where we had a 0 in a row with some non-zero element following it, when we got to that row, we replaced the 0 with epsilon, then we completed the table using epsilon in place of 0, then we took the limit as epsilon went to 0, and then we counted the number of right half plane roots. But we also knew that this was unstable right from the beginning because we had that 0. In the second case, where we had a row of all zeros, we assigned the row above it as the auxiliary polynomial p. Then we took the derivative of p with respect to s, and we replaced the all zero row with that derivative. Then we just completed the table as usual, and then just assessed the stability of the system, either unstable or marginally stable.